Hey guys, welcome to a new video in this computer vision tutorial. In this video here, we're going to talk about stereo vision geometry, and I'm going to show you a code example of like how we can use stereo vision geometry to calculate and estimate the depth of different kind of objects in an image. But first of all, here I have linked the Discord server down in the description, so make sure to check that out. And if you want to join our community where we're talking about some different kind of stuff within computer vision, artificial intelligence, deep learning, and etc. So if you're interested in that, or you have some problems in a project, or you just want some inspiration, make sure to go into the Discord server and check it out and chat with the other community members. So I'll link to that in the description. First of all, here we're going to have this recap from stereo vision. Which is a video that I've already made. So we can see over here to the right, this is the thumbnail for the video that I've already made. So if you want to go more in depth with computer vision and get like started and introduction to stereo vision, make sure to check that video out first before we go into this one here, because we talked about like the basic stuff and an introduction to stereo vision, where we talked about some different kind of 3D sensors for stereo vision. So we can use like monocular camera, but we can also use some time of flight camera, where we have a laser, or like an infrared LED, or like some other different kind of sensor to have the 3D sensor, so we can actually like get the depth of different kind of objects in our image. And then we also talked about like how we can estimate the distance using stereo vision, and we're going to continue with that in this video here, and we're going to dive more deep into like the actual like geometry and how we can calculate the disparity. And then I'm going to show you in a code example of how we can set all of these things here up in code, and how we can use it in an actual like real life application, where we're going to calculate or estimate a distance to an object that we're tracking in the image. So when we're estimating the distance during this derivation, we first of all we need to calibrate our cameras. So we need to get the intrinsic and extrinsic parameters for our camera. So we need to calibrate our camera, so get those. And I've also made a video about that, so you can go check that out if you want to like know how to calibrate the camera before we're going to use all of these different kind of stuff here. And then after that, we're going to create an epipolar scheme by using epipolar geometry, which we also went over in the stereo vision video. So like how we can have this multiview geometry, where we have two image frames, and how we can like relate those two to each other with epipolar geometry. And then after that, we're going to build a disparity map. So we're looking at the disparity from image frame 1 to image frame 2. And then from the disparity map, we can actually like calculate the depth with some of the parameters that we have for our camera. So that way it was more like an introduction to the disparity and depth maps, and then we're going to dive more deep into it in this video here, and then we're actually like going to show you how to do it in code. And then we also talked about epipolar geometry. So first of all, here we're just going to talk about camera calibration and have a like short recap of what we already went over in the camera calibration video. So we're calibrating our camera to remove distortion, so we get like a better image that we can work with and do operations on. So we have these different kind of distortions in our images. It could be, for example, like barrel distortion or pinhousen distortion, and it can be caused by the camera lens, or if we have like a fisheye camera. And we also have something called tangential distortion, and it is when our like image plane is not parallel to the optical axis of our image, and then we'll actually like get an uneven magnification of this, like for example barrel distortion here. So we can use camera calibration to actually like undistort our image, as we can see over here to the right. Then we have an original image here where we have this barrel distortion on our image, and then by calibrating our camera with this chessboard here, we can actually like calibrate our camera, so we get some different kind of like distortion parameters and our camera parameters, and then we can actually like undistort our images, so we get the image over here to the right instead, and then we can actually like do good calculations and estimations with the undistorted image over here. So this is really useful and very important when we're talking about stereo vision, because we want to calculate like the exact depth or like distance to an object in an image. So now we're going to talk about like what are disparity and depth maps. So here we have an example here where we have a scene here where we take an image from two different cameras, and they're aligned at the same axis. So they need to be like at the same axis, like on the same x-axis, and then we're taking, then we know the distance from that, and then we have two images where we see this exact same point in the image, and then we can actually like, because if we only have one camera, we don't have any information about depth in the image. But if we have like a scene that we see from two different kind of images, or like two cameras, then we can actually like get the depth information in those images. And when we have these different kind of points here, we can actually like, from two image views, we can actually like calculate the disparity of those points in the image related to the two images that we take from the two cameras. and then we can get this disparity map here, which is the disparity from like that point to the optical center of that image, and we do that for both images. And then after we have calculated the disparity map, then we also have some information from like for example the focal length and stuff like that from the camera. And when we know these parameters here, we can convert it from a disparity map to a depth map. So we can see over here to the right we have a depth map where we actually like have the exact depth or like distance to that object in the image that we see from the two cameras. So we're going to use this to actually like track an object in the code later here in the video here, and then we're going to calculate that depth by calculating disparity, and then after that we're actually like calculating the depth from some of the parameters that we have from our camera. So now we're going to go in more into like how this multi-view geometry works with the disparity. So I made this figure over here that like illustrates how a point is moving around in two image frames and how we can see them from both image frames. So first of all, here we have a camera left here and a camera right, and then as I already talked about, we have this baseline here where the two cameras is at the same axis, but they have like a distance from each other, so we actually like need this baseline information here. So we need to have the exact information about like how far away are these cameras from each other. And then we also have this focal length here, so we're taking we take a standpoint in the pinhole model. So we have this focal length here from the camera lens to the actual like image plane. So this line here will be the image plane where we just combine it. So they may be split up here, and we'll have some different kind of points here that one of the cameras can see. So we have the left image frame over here to the left and the right image frame over here to the right. And then we have like this depth here of the image, like how far away our camera can see, which is C. And then we have this X value here, which is the distance from the left optical center here to the point that we're actually like going to find the disparity for. And then we have this X and L, the left disparity here and the right disparity here for a given point that we want to calculate in our image. So here in the red we have a point here that we're actually like going to calculate the disparity for in this simple example here. And over here to the right I have these different kind of formulas here like that we can use for actually like calculating the disparity in our image. So we can see we have this C divided by F here, so F is the focal length, so it will be the ratio over here. And then we have this X here, which is divided by this disparity here, and then we can actually like calculate the C value here by just multiplying with the focal length on both sides. And then we actually like get the depth, the longest depth that we can actually like have in our image. And we can do the same thing over here for the X right here, which is the right disparity. And the only difference here is that now we just have X minus B because we have moved our right camera a distance of the baseline to the right here in this example. So it will be X minus this baseline down here. And then if we play around with these different kind of formulas here and we have this XL here to the left of the equation, then we can actually like calculate the disparity here with this X value here that we have and the C value, and then multiply that by the F value here. So then we'll get this value here, which is this disparity of the point. So we will actually like have a point here which is on the image frame, which corresponds to this 3D world coordinate up here. And then we have this disparity here, which is the distance from the optical axis for the camera and then out to the point here, which is intersecting in the image plane. So this will actually like be the disparity of the point in the left image frame, and we can do the same thing over here for the point of the disparity of the point in the right image frame. And then when we subtract these two from each other, so we have this disparity in the left point here and the right point here, and then we can subtract them from each other, and then we'll get the actual like disparity of the different kind of like points that we want to find in our image. So in this video here, we're also going to have this depth estimation code example where I'm going to show you the code, like how we can actually like do this depth estimation here, and we're going to track an object where we convert the frame to HSV, so we can actually just track a color in the image, and then we can calculate the depth to that object in the image. So this is just like an introduction to what we're going to cover more in later in this video here, where we're actually like going to see the code example. We're going to run the code example and see how we can estimate the depth in an image by using stereo vision. So another approach we can take, and this is just a short introduction and just to like give you an idea of what we else can do to do this depth estimation. And I'm probably going to do a video or like a series of videos later on where we're going to use neural networks to actually like do the estimation of the depth in images. So we have this two different kind of approaches here that we can take with neural networks. So for example, we have a left image here from our stereo vision camera, and we have a right image here, and then we have this depth CNN where we pass these two stereo vision images to our depth CNN, where the depth CNN is trained on actually like disparity maps or depth maps from images, and then we can pass these new left images and right images, and then we can actually like get out the disparity maps and for both the right and the left image by using these convolutional neural networks. So another approach is to like actually like train our depth CNN here. If you only have a monocular camera and we want to do depth estimation, then we can actually like train our depth convolutional neural network with two disparity maps or like two disparity images and trying to estimate the depth from those, and then train our neural network on that, and then only pass one image if you have a monocular camera to that CNN that is trained on stereo vision images to calculate the disparity map, and then we can actually like estimate the disparity image from a monocular camera by using convolutional neural networks as well. So it really depends on your situation and what you won't get like as good a result by only having a monocular camera where we can like estimate the depth. But if we don't need like really precise values, then it's a really nice and cool example to take with only a monocular camera instead of using this stereo vision where we need two cameras as an example up here above. So I just wanted to show you this drawing here that I did of this multiview geometry where we have a point here where we're calculating the disparity for. So for example, if we move the point here around, like we can see that disparity is changing, and we can use this information here to actually like calculate the depth in the image. So if we move the point here really close to the image plane or like to the camera, then we can see like the changes in disparity here is great. Like it's greater than if we're moving far away. So we can see like if we're really far away here and we're changing like the point here, like the change in disparity is not really that great. And this is like how we can actually like get the information from stereo vision to have this information about the depth of the objects or like objects or points in our image. So if I align this point here with one of the optical axes here, we can actually like see how it changes in the right image frame. Like if we're moving closely, like if we for example have the point here, we won't be able to see it in the right image here, but we can see that the disparity here is greater the further we move away here from the image frame or from our camera lens. So this is like how we can actually like get the information about the depth in images by using this stereo vision. So we're not into the code here, and this is an example and a code example of like how we can actually like do stereo vision depth estimation in C++ here. I'm also going to do this project or like this kind of like project or code example here in Python, and then I'm going to show you a video about that as well. So if you want to use it in Python instead, but in this example here in this tutorial, we've mainly been focusing on C++. So this is what we're going to do first. So first of all, here in this project here, we are going to like have an object detection where we're going to do some finding of some contours, where we're going to track a circle in an image, and then we're going to calculate the depth of that circle when we're moving it around and moving it closer and farther away from the camera. So this can be used for a lot of different kind of projects and applications. So if you have some objects, like it could be cars that are driving around, and we want to calculate the depth of those, then we will probably have a neural network or some other different kind of object detection algorithm running, and then we can actually like use stereo vision together with that object detection algorithm to actually like calculate the depth or the distance to some certain or like some different kind of objects in the image frame. So first of all, here we're going to include OpenCV here as we always do, and then we use this iris stream here and the vector, and then I've made a class here for stereo vision where we're actually like going to implement different kind of functions that we're going to use to calculate the depth and the stereo vision application. So first of all, here we need some different kind of parameters that we need to specify for our stereo vision camera. So in this case here, we have a baseline of 7 centimeters. So this is the distance between the two cameras, and then we have the focal length here, which can be found by doing camera calibration or in the specifications of your camera. So the focal length here in this case here is 6 millimeters, and this is the distance from the lens to the actual like image frame. And then we have this alpha value here, which is the field of view for your camera. So first of all, here we're going to have this left frame here and the right frame. So we have this matrix here with the left frame and the right frame, and then we're going to use this video capture cap left function here, which is going to actually like open up the cameras in C++ here and OpenCV. And then we create an object here of our stereo vision class where we pass these parameters here of the baseline, the alpha, and the focal length. So let's now jump into the stereo vision header file here, and I'm going to show you like different kind of functions that we're going to implement to have this stereo vision code running. So first of all, here we have this, we just have this constructor here where we just set these baseline alpha and focal length here to some member variables down here that we can use in our code. And then the first function here, or like the first method here that we're going to implement is on the stored frames. So we're going to calibrate the frames. And I've already made a video about that, like how we can like calibrate a camera and how we can get the camera matrix and like the distortion parameters and stuff like that. So we won't dive deep into like how we can calibrate cameras, because you can just go back and look at the video that I've already made to actually like calibrate the cameras before we're doing all of these other different kind of operations on the images to get more exact results. But this is just an example, like and I want to show you like how we can actually like do this in code, and this will just be like an example that I'm going to show you. So second off here, we're going to add an HSV filter, because we're going to calculate, we want to segmentate out a certain color in the frame. So it will be a red item in this case here. So we want to convert it to an HSV color space first. And then we're going to actually like filter out that specific color that we want to like segmentate, or like that we want to track and detect in our image. And then we're going to actually like find the circle or like border object that we want to detect. So we only find the largest one in this case here, and so we reduce the false positive. So in this example here, we're just going to track one object that we're finding in the image, and then we're going to drag it around in the image and then calculating the depth to that object with our stereo vision setup. And then we have this find ball here, which is just like, we're just going to do some finding contours, and then we're going to do some different kind of method to like find the center of that contour, like the center of gravity for that contour. And then second here, like the last method here that we're going to implement is the find depth. So like we're actually like going to find the depth for this ball or like this item that we're tracking in the image. So we want to find the circle of our like contour that we find, and then we want to find the depth for that center of the contour that we found in the image. And then we're going to calculate depth from the different kind of formulas that I have in the video and that I just showed you from this multiview geometry, where we have a point that if we're moving around in the image frame, and then we're calculating the disparity of that object or like that point in the image frame. So if we go into the stereo vision C++ file here, these are the actual like implementations of the method here. And this understored frame here is just the camera calibration, and we won't go into depth in this video because we've already been over it and it's a fairly long process. And then we're going to add this HSV filter here, where we're going to take in the frame from the camera. So this will both be the left and the right. So we're going to call this method here twice. And then we're going to specify what camera is it the left or the right camera that we're passing this HSV filter here to. And you don't really need to specify this, because like if you have like similar cameras, but in this case here, just for demonstration purpose, I don't have like two identical cameras, so I need to specify this camera parameter here as well. Then first of all here, we're going to use this Gaussian blur here, just to blur out the frame to reduce the noise in the image frame. And then we're going to use this convert color here to actually like convert it to HSV from BGR color space. Because if we wanted to segmentate out one color, it is good to just convert it to HSV, because then we can just use the hue value to actually like do the extraction. Then we're going to have this mask here, which is the actual like segmentating of that color that we want to segmentate out in the image. And then we calculate a lower limit for like the red color in the right image frame, and we're going to calculate an upper limit for the red item in the right image frame here as well, and we do the same here for the left image. So in this case here, it's just trial and error, and I just went in and saw like the thing that I had in the presentation, and then we find the value for the red color that we want to segmentate out from the image, and then we just like play around with these parameters here until like we find the exact one that extracts that color that we want to. And then we have an if statement here that just checks if it's the first camera, then we use the lower limit for the right, or else we use the left, it is the left image frame here. So we use this in range function here to actually like segmentate out the colors that are within this range here that we specified up here. So this is the red color that we want to like get from this in range function. And we're going to store it in this mask matrix up here, or like this mask frame up here. So we can like do some operations with that later on. And then we're using some morphology operations where we're going to use opening to reduce some of the noise in the image. So first of all, we're going to erode the mask here with a kernel of 3x3, and then after that, after we have eroded our image or like the frame, we're going to dilate it. So this is just a morphology operation, so I can like do opening and to reduce the noise in the image for this mask here, or else we'll get a lot of like false positives around in the image. So it's just to like do more image pre-processing to get like a better result when we're going to do finding contours and then calculating like the center of mass for that contour. So to find the ball here, we're going to pass the frame here and the mask that we're calculated up here with this HSV filter. So first of all, here we're going to have a vector of points where we're going to store the contours that we're finding in the image. And then we use this function here, find contours, to actually like find all of the contours that we're tracking in the image. And in this case here, we're finding the contours in the mask. So this will only be finding contours of that color that we have segmented out in our image or like in our mask here. And then we're going to store the results here in the contour, and these are just like some default parameters that we can specify for like how we want to find the contours in the image. Then we're going to sort the contours here so we get like the biggest one. So we're only interested in like tracking the biggest contour in the image that we're tracking currently. So first of all we sort the contours here, and now we have it in sorted order, and then we can actually like take the last element of the contours here, and then we have the largest contour that we tracked or like detected in our image. Then first of all here we check if there's any contours that we have tracked in our image before we do all of these different kind of calculations down here. And then we find the largest contour here, which I just told you is the last element in this contour vector here. So now we have a vector here of points where we have this largest contour here that we have tracked. Then we want to find the center of that contour, and we want to find the radius in case we're tracking a ball. And then we can use this min enclosing circle here. So we actually like we can actually like see down here, it finds a circle of the minimum error enclosed at a 2D point set, and the function finds the minimal enclosing circle of a 2D point set using an iterative algorithm. So this is just like, so we find a circle which is enclosed, so the minimum of that, and here we pass the largest contour that we have found and the center here where we're going to store the center point that we have tracked in our contour. And we're also going to extract the radius from this min enclosing circle from function in here. So now we actually like have the center and the radius of the largest contour that we have tracked in the image. And then after that, we're going to use this moments function here, where we can actually like find the center point of the contour that we have tracked. So now we're not only finding the center, but we're finding the center point, which is the center of mass of the contour that we have of the contour that we have tracked or like detected in our image. And then we go down here and see like if our radius of the detected circle or like detected object in our image is greater than 10, then we actually like draw the circle and the center point and the center of our circle or like of our contour on the actual like image, so we can see like what object are we tracking in the image. And then we return the center point here if we're finding a contour in the image, and if we're not finding a contour in the image, we just return 0.0, so we don't find any points or like any contours in our image. So the last function here we're going to like actually like implement before we're going into the main function and see how we can call these different kind of functions here and do the different kind of operations before we're running the program. So up here we're finding depth here, where we take in the left circle that we found and the right circle, so like the objects that we detected in the right image frame and the left image frame. And we're also going to pass the left image frame and the right image frame here as references, because we just want to override that. So first of all, here we have our focal length in pixels here. So we want to calculate the focal length in pixels to actually like do the operations. And then first of all, we check if the width of the right image frame is equal to the width of the left image frame to be able to like do these different kind of operations, or else like if they don't have the same width, like we can't really use stereogeometry in this example here, because then the disparity would just be like really bad. So we calculate the focal length with this formula here, and this is just like a standard one to convert the focal length from millimeters to actual like pixels that we can use. And then we have this x left here and the x right here. So we have this circle right x value. So we find the x value here for our circles that we have detected with our contours. And then we can calculate the disparity here, where we just take the x left and the x right here, and then we just subtract those from each other. And then we actually like have calculated the disparity here that we can use for calculating the depth C value down here. So we have this float C depth value here, which is just this formula is just the exact same one from the presentation. So we have this baseline here that we're multiplying with the focal length, like the focal length in pixels, and then we're going to divide that by the disparity that we have calculated up here from the image. And so like the disparity of the 2 points that we're tracking in the image. So by this formula here, we actually like get the depth in centimeters, and we can return the absolute value from that, because else it will just be negative values at some point when the disparity here is negative. So we return the absolute value here of the like the C depth here. So this is the actual depth, or like the distance to the object that we're currently tracking by finding these contours here in the image. So these are all the methods that we have implemented in C++ here to actually like do the stereo vision and tracking an object around in an image frame, and then calculating that distance, or like the depth to that object. So if you're into the main function here, or like the main file here, first of all, we know that we created this stereo vision object here, and then we just check if one of the cameras is not working properly. Then we just see out like and return -1 here, that we cannot open one of the cameras, for example. So this is just for debugging purposes. And then we have this left mask here and the right mask here that we're going to calculate, and then we have like a resulting frame in the left image and resulting res frame for the right image as well. And then we have these two different kind of points here, which is the left circle and the right circle. So this is the points in the like the two image frames. And then we have this ball depth here that we just set equal to 0. And then we'll have this while loop here that just runs forever until like we terminate our program. So first of all, here we're going to read in like the left image frame to this cap left here, and the right image frame we're also going to read it in from the two webcams, or like the two cameras that we have connected to our computer. So now we have like the left frame here and the right frame where we have from our cameras. And then we could do this calibration here of the frames, and I won't be doing it in this tutorial here because I have two different kind of like webcams that we're going to do. So this is just a demonstration purpose. But if you want to like have the exact the exact distance to the object and like have a really good result of that depth estimation, then you have to like you have to calibrate the frames before doing all of these different kind of calculations here. And ideally you will also need the two same cameras, so identical cameras where we have the same parameters, both the intrinsic and extrinsic parameters. And then we're going to apply this HSV filter here, where we have the left mask and the right mask, where we're just going to like call this function here stereo vision, where we have this object, and then we call this function here add HSV filter, and then we pass in the frame that we want to apply the HSV filter to, and then the camera like in this case here is the 0 camera, and down here is the first camera, and this is just because I don't have identical cameras in this application, or like in this example here. And then we're going to actually like bitwise and the left image frame with like the left mask here that we have, and then we're going to store it in this left resulting frame here that we can then use later on. So this will be like the result of bitwising anding our left mask with our left image frame. So this is like the actual like segmentation of the object that we're tracking in the image. So now down here we're going to detect the actual like circles here, like both the Hoff transform can be used as well, or like some different kind of like neural networks to do object detection. But in this case, if we're just finding contours where we're finding like a ball or some other different kind of objects in the image. And then we just call it with this stereo vision.find ball here, and we store it in the left circle and the right circle here. And then down here we can check if no ball is detected, and if no ball is detected, we just show on the image that the tracking is lost. And if we found like a ball or like an object in our image, then we're going to actually like go down here and then call this find depth function here, where we actually like where we'll get the depth to the ball or to the object that we're tracking in the frame, and we'll just put out this text here that we're tracking an object now. And then we also see out the depth of the ball here, ball down here, so we can actually like see the depth from the stereo vision cameras to the object that we're tracking in the image. And then down here we're just showing out the frames, so we show the left frame and the right frame, and also the mask, so we can see like what object are we segmenting out at that point. And if we hit Q, we'll just break out this while loop here, and we'll terminate our program. And before we terminate our program, we will release the captures for the left image and the right image, and we will store all windows. So I've not set up the stereo vision setup here, and we're going to run the program here so we can actually like see what this application and project does. So we get up the left image frame here and the right image frame, and we get the two masks down here where we're going to segmentate out a color. So in this case here we can see that these two cameras here are not identical, and like the colors is not exactly the same, because that's why we had these different kind of upper and lower limits for our HSV filter. But if I have an object here, which is a red object here that we're going to track in this image here, and we can see that we're tracking it really good here in the left image frame and the right image frame, and we can also see like the two masks down here is really good, and we're tracking the object really good here in the image. So we can see that we're now calculating the depth over here to the right, where we have like around a meter from the object to the camera here, which is really exact when we're considering that we haven't calibrated our cameras. And this is just like a short and demonstrational example. So if I move this object here closer to the stereo vision setup here, we can see that now we are like half a meter away from the cameras, which is really exact actually. And then when we're moving closer, we can see that the ball depth here gets less, and then when we're moving farther away here from the camera, then the depth of the image gets greater, or like of the object that we're tracking. So this is a really good estimation of the depth by using this stereo vision camera setup that we've just set up, and which is really kind of like simple code example in C++ here. And as I already mentioned, I'm going to do this here in Python as well, and then I'm going to show you like how we can do it in Python. But in this example here, we're using C++, and we can see that this is a really good estimation of the object here that we're tracking with this stereo vision setup here. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification under the video here, and also like this video here if you like the content and you want more of these different kind of like applications and projects in the future. And I really appreciate your support. It helps me and the YouTube channel out in a massive way. So I'm currently also doing a neural network tutorial and like deep learning tutorial. So if you're interested in that, like we're going over the basic things right now, and then later on we're going to cover more like complex things where we're going to use convolutional neural networks together with computer vision and a lot of other different kind of stuff like that. So if you're interested in that tutorial, I'll link to it up here, or else I'll just see you in the next video, guys. Bye for now.